Hello everyone. Let me begin with a simple question. Have you noticed how a ball always falls to the ground, how electric bulbs always glow when connected properly, or how stars continue to shine for billions of years? These are not accidents, they are governed by physical laws. Physicists explore the universe from the tiniest particles smaller than atoms to the largest galaxies, searching for these laws. Some quantities in nature change with time, while others remain constant. Those that remain constant are called conserved quantities. Conservation laws, like energy, momentum, and charge, are the backbone of physics. They hold true everywhere in the universe, whether in a lab experiment or in the life cycle of a star. Let's start with a familiar one, the conservation of mechanical energy. When a body moves under a conservative force, such as gravity, the total mechanical energy, that's kinetic energy plus potential energy, remains constant. Take the example of a freely falling object. As it falls, potential energy decreases while kinetic energy increases. But the sum stays the same. In symbols, we write E equals K plus P, and that value is constant. Just before hitting the ground, the entire potential energy has been converted into kinetic energy. Applications: roller coasters, pendulums, and even planets moving in their orbits rely on this principle. Now, let's take it further with the conservation of total energy. Even when mechanical energy changes into other forms like heat, sound, or light, the total energy of an isolated system remains constant. For example, when a ball falls to the ground, its potential energy is partly converted into sound, heat, and vibrations. But if we add everything together, the total energy remains the same. Then Einstein brought a revolutionary idea, mass-energy equivalence. He showed that mass and energy are not separate, but two sides of the same coin. His famous equation is delta equals open bracket delta m close bracket c squared, where c is the speed of light. This means if a particle loses mass, an equivalent amount of energy is released. A striking example is when an electron and a positron annihilate to form photons. Another universal law is the conservation of momentum. In an isolated system, the total momentum remains constant if no external force acts. Linear momentum is mass into velocity, written as P equals m times v. Angular momentum, too, remains conserved. Think about the recoil of a gun. When the bullet moves forward, the gun moves backward, total momentum before and after remains the same. Or a skater pulling in their arms. As the arms move closer, the skater spins faster, conserving angular momentum. Next comes the conservation of electric charge. The total charge of an isolated system never changes. Charge can neither be created nor destroyed. For example, rub a glass rod with silk, the rod gets positively charged and the silk gets equally negative. Net charge is zero, both before and after. Similarly, in nuclear reactions, the total number of nucleons, that is, protons plus neutrons, stays the same. Take uranium-238 decaying into thorium-234 and an alpha particle. The nucleon count is 238 before and after. The balance is perfect. Equation: uranium-238 gives thorium-234 plus helium-4. Now here's something truly beautiful, the deep connection between symmetry and conservation laws. Symmetry in time means that laws of nature don't change with time. If you perform the same experiment today or next year, under the same conditions, the results will be identical. This symmetry corresponds to the conservation of energy. Symmetry in space means the laws of nature are the same everywhere. This gives us the conservation of linear momentum. Isotropy of space, meaning no preferred direction, leads to the conservation of angular momentum. From the lab bench to the farthest galaxies, these symmetries show us that the universe is deeply ordered. So, let's quickly revise what we've learned today. Physical laws describe how the universe behaves. Some quantities change, but conserved ones, like energy, momentum, charge, mass energy, and nucleons, remain constant. We explored how these laws connect to real-life phenomena, from a falling ball to nuclear reactions in the sun. And we discovered how symmetries of time and space are directly tied to conservation laws. Conservation laws are not just equations, they are the backbone of physics, helping us explain everything from atomic particles to galaxies. I hope you now have a better sense of how these laws hold the universe together. See you in the next session with another fascinating concept of physics.